Hi everyone, welcome back to Chem Help ASAP. In this video, we are going to consider the kind of interactions that occur between polar molecules. Now, once we have taken a look at that, we are also going to throw some nonpolar molecules in the mix and see what happens then. So let's get started. Let's start, of course, with our definition of our intermolecular forces. Again, these are the attractive and repulsive forces that occur between molecules. Now, today we are going to be talking about dipole-dipole forces. These are the attractive and repulsive forces that occur between polar molecules. So you'll remember, a polar molecule is a molecule with a permanent dipole moment. I'm going to draw a generic polar molecule. It has a positive end and a negative end. Now, when this polar molecule is in proximity to other polar molecules with a permanent dipole moment, they are going to arrange themselves such that they set up attractive forces between each other. So there will be an attractive force here and an attractive force here. Of course, if we are talking about polar molecules, say in a liquid state, there would be lots of them around. And they are going to try as much as possible to orient themselves to maximize these attractive interactions. However, it's not always going to be attractive forces. You can see here that this would be a repulsive force there. But still, overwhelmingly, we are setting up attractive forces here between the molecules. Because polar molecules have this permanent dipole, this attractive force between the molecules is much stronger than the London dispersion or induced dipole forces. So let's take a look at some actual examples. Let's take a look at the difference in boiling points between ozone and sulfur dioxide. You can immediately see that ozone boils at a much lower temperature than sulfur dioxide. So let's see if we can explain this with intermolecular forces. Here is the Lewis structure for ozone. Its shape is bent. It is a nonpolar molecule. Because we have 3 oxygens bonded together, there are no polar bonds. There's no difference in electronegativity here because it's an oxygen bonded to an oxygen. Here is the Lewis structure for sulfur dioxide. It is also a bent molecule, but in this case we have polar bonds. The oxygen is more electronegative than the sulfur. So these bonds are polarized. This means sulfur dioxide has an overall dipole moment. It is a polar molecule. This means the dominant intermolecular force in ozone are your London dispersion forces. While in sulfur dioxide, your dominant force is going to be dipole-dipole. Because dipole-dipole forces are much stronger than London dispersion forces, this means that sulfur dioxide's boiling point is much higher than ozone's. Now, if we were to mix these 2 molecules, you would have sulfur dioxide with its permanent dipole. Here comes ozone. It has no permanent dipole. However, the dipole on sulfur dioxide will induce a dipole on ozone. So you get a dipole-induced dipole effect. You can guess that this is stronger than pure London dispersion forces. However, it's still going to be weaker than your dipole-dipole forces. You now hopefully have a better understanding of how important dipole moments are. They have a huge influence on how molecules behave and also help us understand how molecules influence each other and interact with each other. I hope you found this video helpful, and thanks so much for watching.